Welcome to Structural Dynamics class. In this class, we will discuss how to solve the equation of motion for multi-degree of freedom systems. So, the outline of this lecture is we will discuss about how the idealization has taken place and then dynamic equation of motion, solution of equation of motion, and then we will solve one example problem in this. Now, if you look at a building, a complex system that can be idealized as number of degrees of freedom as many as number of floors. So, in this example, you can see a building which is of 3 floors. So, we are converting that into 3 lumped mass system. So, 3 degrees of freedom system. So, this is idealization. So, we can calculate mass from this floor properties. So, mass of each floor M1, M2, M3 and stiffness of each floor K1, K2, K3, damping from each floor C1, C2, C3. Then we wrote equation of motion, that is mu double dot plus cu dot plus ku is equal to P of t, which is a function of time, force. Now, we have discussed already that how to generate mass matrix, how to generate stiffness matrix and how to generate damping matrix. So, mass matrix is M1, M2 and M3 with off diagonal terms as 0, K1 plus K2 minus K2, 0, minus K2, K1 plus K2 plus K3 minus K3 and K3. This is stiffness matrix and then damping matrix in the similar manner as stiffness matrix. So, these are 3 matrices: mass matrix, stiffness matrix and damping matrix. So, we had already discussed that these matrices are positive definite. So, positive definite means if we take the determinant of these matrices, this will be more than 0. So, that means positive value will come. And then this look at this one, in this one off diagonal terms are 0 in mass matrix. So, the reason for that is, so we are putting degrees of freedom here only, the center of mass, and then mass of first mode is not vibrating in the mass of the in the direction of the second mode. So, this we will discuss in the next class about how mode shapes are helping us to understand the complex vibration of the whole structure into simpler manner. So, this K1 plus K2, here you can see there are off diagonal terms. So, this is we can call this as coupled in the form of in stiffness and coupled along damping. So, it is uncoupled along mass matrix. So, in simple words we can say that when we write these 3 equations of motion, so 3 equations of motion for each point mass, we cannot solve these equations independently. Why? Because when we have, say here mass 1 is associated with acceleration 1, but here when we come to stiffness of this first term is associated with the displacement of first mass, second term is associated with the displacement of the second mass. So, that means what, in one equation we have u1 terms and also u2 terms, and in another equation we have u2 terms and also u3 terms. So, that is how we cannot that is the reason why we cannot solve. So, we need to employ special techniques for solving it. Now, how do we solve? So, if we remove say damping and then take it as a free undamped vibration, so we are left with this equation, that is mu double dot plus ku dot, as in you can see here. Now, the response is dependent on both time and location of the mass. So, that means what, u is a function of time as well as location. It is something like, as you can see, this is a multi-degree of freedom system building, idealized system. So, if this building is vibrating, so if we say displacement u, we have to first specify where we are talking about. So, at different floor levels and then at different times. Yeah, if we take the structure like this, now when we say displacement, where are we talking displacement, which location and which point of time. So, at what time. So, suppose this is floor 1, floor 2, floor 3 and floor 4 here. So, we are saying that in lumped mass system, we are saying that at this location and also at this point. So, that is the reason why our displacement function has 2 items in it. One is location and the second one is time. So now if we look at the displacement function, that is u is a function of space, that is location, and it is also a function of time. So the equation of motion u is called coupled equation. Why it is coupled equation? Because in one equation we are having say u1 terms and u2 terms, also u3 terms. So that's why there is a coupling. So we need to decouple it. So for decoupling the equation, so we are using say u x of t, so x and ut, that we are converting that into say phi of x and q of t. Is a space variation function and q is the time variation function. Now in case of multi-degree of freedom system, the value of x are discrete, and but in case of continuous system, this value of x can be any value from 0 to the total height of the building or the structure. So this is discrete and is defined at the location of mass. So now how do we, if say u is equal to phi of x and q of t, okay, how do we define velocity? So we differentiate it once. So if we differentiate it once, since this is a space quantity, we cannot differentiate, it will be there. Then q is q dot of t. Then acceleration u double dot x of x comma t is equal to phi of x q double dot t. Now what is q dot? So q dot is nothing but, say if a structure is vibrating, so it is vibrating in simple harmonic motion. So we can write that simple harmonic motion as qt is equal to a cos omega nt plus b sin omega nt, as in the case of single degree of freedom system. So we know that this represents simple harmonic motion. Now if we double differentiate this one, so what we get is q double dot is equal to minus omega square a cos omega nt and then minus omega n square b sin omega nt. So that means what? Omega minus omega n square q we get. So that's how is written here, that is what is written here. So that means what? U double dot t is equal to minus phi of x omega n square q of t. So that is written. Then if we take this and substitute the values in this equation, basic equation, so what we get is mu double dot, so u double dot is replaced with this minus phi omega n square q plus k, so phi q. Then if we rearrange the terms, what we get is k minus omega n square m multiplied by phi and q. It should be equal to 0. So for non-trivial solution, q cannot be 0. So if q is 0, there is no solution. If q is 0, then there is no solution. So that will give us k minus lambda m into phi is equal to 0. So lambda here we are representing as minus omega n square. So minus lambda is minus omega n square. So yeah, lambda is omega n square. Then for non-trivial solution, phi also cannot be 0. So if phi is 0, solution is 0. If q is 0, solution is 0. So what we want is q is non-zero term and phi is also non-zero term. So in that case, so what we need is k minus lambda m should be 0. So determinant of this k minus lambda m should be 0. So this is called characteristic equation. So we need to solve this characteristic equation to get characteristic roots, characteristic vectors. So that is lambda, we get say as many number of degrees of freedom it has. So if it is 3 by 3 matrix, we get 3 lambda values, and corresponding lambda values what we can put is lambda 1 here and solve for phi. So we get phi 1. So lambda 2 corresponds to phi 2, lambda 3 corresponds to phi 3. So these are eigen values, and phi 1, phi 2, phi 3 are called eigen vectors. So we will discuss about this eigen vectors in detail in the next class. Now some properties of characteristic equation. So this can also be called as frequency equation or frequency equation. So this frequency equation, it has n real roots. So if the matrix size is say n by n, it will have n real and positive roots. Now why? Because k and m are symmetric and positive definite. So for that reason we will have n real roots. The roots of characteristic equation are also called eigen values. They can also be called as normal values or characteristic values. So, when natural frequencies are known, there can be corresponding vectors as I told you. So, for lambda 1 natural frequency or eigenvalue, there is one vector, that is phi 1. So, for lambda 2 phi 2 we can get, for lambda 3 phi 3 we can get. Now, let us solve that, use this one, and let us solve one example problem using for understanding multi-degree of freedom systems in a proper manner. So, let us take a structure. Okay, it is a real regular structure. So, details of the structure are, say, 3-story building with 3 meter by 3 meter plan area. Okay, the properties are as follows. So, floor to floor height is given as 3 meters, column dimensions 230 by 230 mm, and then thickness of slab 100 mm. And perform eigenvalue analysis and find out eigenvalues and eigenvectors by assuming columns are massless and then infill walls are not present. So, we are taking these assumptions for simplifying the problem. Now, let us solve it. First, let us find out mass. So, mass at first floor. So, that is 3 meter by 3 meter is given. So, and multiply by 0.1. So, this will give volume of mass, and then this is weight density. So, if we get weight density, so 22.5 kilonewton weight, that we can convert as 2250 kg mass in all floors. So, multiply by 1000 and divided by 9.81. So, we get 2250 kg. All masses same. And then we want stiffness. So, for that we want modulus of elasticity. So, it is assumed that the material grade is M25 grade concrete. So, 5000 under root FCK. So, we get 25,000 Newton per millimeter square as modulus of elasticity. And then moment of inertia of the column cross section. So, since it is square cross section, so both sides the same. So, we are taking BD cube by 12. So, that is 230 power 4. So, this is also 230, this is also 230. So, that is why 230 power 4 by 12. So, 233.2 multiplied by 10 to the power of 6 mm power 4 is moment of inertia. So, now we need to calculate stiffness. So, stiffness of one column is 12 EI by L cube. So, since 4 columns are present on each floor, so we take 4 multiplied by 12 into E is 25,000. So, we are substituting it here. I we are substituting from this, divided by H cube. So, H is or L cube. L is 3 meters height. So, total stiffness value is this. Stiffness value of floor stiffness this is. Since all the floors are similar, same. So, this value is same in all the floors. Here you can observe that we have converted this into Newton per meter. Then we calculate eigenvalues. How do we calculate eigenvalues? By using characteristic equation. So, we have stiffness matrix as we have generated from the earlier class. So, K is equal to K1 plus K2 minus K1 0 minus K2, K2 plus K3 minus K3 0 minus K3 K3, and then mass matrix is also there. So, we have this stiffness matrix. So, if we plug in the values here, so we get stiffness matrix. And then mass matrix. So, mass same, all masses are same. So, we have mass matrix. Characteristic equation can be written like K minus lambda m is equal to like this. So, here you can see lambda values are there, lambda values. Now, we need to solve this matrix, that is take the determinant of this. Okay. So, if you expand it, it will look like this, and then further expansion, and then so if you solve it, then what we get is this quadratic equation, okay, cubic equation in fact, not quadratic equation, cubic equation. Lambda 1 we have, so and we get Tn, so natural period of say corresponding to each lambda, so that is 2 pi by omega n. So, lambda is equal to under root of omega square. So, lambda 1, lambda 2, lambda 3. Oh, in fact, lambda is square of this, lambda is square of omega. Okay. So, in fact, lambda root is omega. So, we get omega values. So we get omega 1, omega 2, omega 3. So this is eigenvalue 1, correspondingly we get natural frequency, that is 30.198, and corresponding natural period is say 0.2 seconds. So lambda 2, so we will get omega 2, corresponding natural period is 0.074 seconds. Lambda 3, third eigenvalue, so we get third natural frequency and we get the third natural time period. So we can clearly see that these natural frequencies are spaced. So usually in regular buildings, these values will be in the order of 1:3:5 order. So 1:3:5 order. If it is a regular building, we will have values like this: omega 1, omega 2, omega 3 will be in this order. So omega 1, omega 2, omega 3 will be in the order of 1:3:5. They will not be exactly in this order, but almost around that values. Now if we calculate eigenvector corresponding to lambda 1, then we get, so this is corresponding to lambda 1. So you can see this 1.802, 0.445 value. So if you solve this one, as you can see, let me explain you that k minus lambda m into phi 1 is equal to 0. So this is k minus lambda. So this lambda m value is already substituted here. So we got this. So in this one, so first one 18.67 into phi 1 minus 10.36 into phi 2. So this will have phi 1, phi 2, phi 3 three terms. This will have phi 2 and phi 3 terms. So what we can do is from equation 1, so we have to assume some one value in this one. So in equation 3, since it is representing the roof of the structure, at the roof level of the structure in the first mode, so we are assuming this value as 1. So if we assume this value as 1, so relatively we get phi 2 of first mode. So we get that value. So that is 0.82. Again we take phi 3 and phi 2 values and substitute in the second equation. We get phi 1 value and put phi 1 and phi 2 value to check whether they are matching or not. So that's how we get, so phi 1, phi 2, phi 3 of first mode, and we get mode shape if we plot like this. So this is 1, this is 0.8 and this is 0.445. So usually first mode will touch the axis. This is the axis of the building at this location only, at the base only. It will not touch anywhere. Now when we check the lambda 2, that is second eigenvalue, so we get second eigenvector. So second eigenvector is, you can see this one. So it is crossing the axis at one point, this is the beginning, and then it is crossing at only the second location. So these two, okay, in first one eigenvector, it touches axis only at one point and at no other place it touches, and the second one it crosses at this location and it touches the axis at this location. So when you substitute eigenvalue 3 in this equation and get eigenvector values, so phi 1, phi 2, phi 3 of mode 3, so we get it like this. So you can see this one is crosses the axis at one point, second point, and this is the beginning. So 3 places. So if we look at all 3, at a time, so this is phi matrix, that is values matrix. Okay, so the 3 eigenvectors are there. So this is called mode shape matrix. So first mode, second mode and third mode. So first mode vector, second mode vector, third mode vector. So if we represent all these 3 in a location in the same place, so this is the total idealized mass of the building, or so idealized building. So first mode is represented like this, second mode is represented, and third mode is represented. So usually if the top value as say 1, if we normalize it to 1, it has its advantages. So each mode shape will carry some mass of the building in its vibration. When it is vibrating, mass participates in this one. So how much mass is participating in mode 1? how much mass is participating in mode 2, how much mass is participating in mode 3. We will discuss this in the next class. So, first mode, second mode and third mode. So, these modes give the decomposition of complex displacement behavior of the structure into simple idealized structure. Multi-degree of freedom system, or say 3-story building, is oscillating in the first mode. So, all three, so this slab and this slab, all three will be in the positive direction, one direction on the left side direction. And then if it is oscillating in the second mode, then this will be in the right direction and this will be towards left of the axis. And if it is say vibrating in the third mode, then this will be in the right direction, this will be in the left direction and this will be in the right direction. So, this is a concept of mode shape in the building. So, if I oscillate it slowly, so then it will get excited in the first mode. If I increase the frequency, then it will excite in second mode. If I further increase its frequency of excitation, it will move in the third mode. In summary, what we have studied in this class. So, we have studied how to formulate mass matrix and stiffness matrix, and how to solve the characteristic equation, and then how the solution of the characteristic equation is represented in the form of eigen values. So, eigen value is nothing but the frequency of the structure in each mode. So, first mode, second mode, third mode. So, omega eigen value 1 represents the frequency of the structure in along first mode, and second mode is second eigen value and third mode is third eigen value. So, this is representing the frequency, and then the mode shape is there. So, mode shape is representing the deflection profile of the structure, deflection profile of the structure in first mode, deflection profile of the structure in second mode, deflection profile of structure in third mode. So, this mode shapes have some important properties, so with which we can understand the behavior of the structure under the action of dynamic loads in much better manner. So, we will discuss about mode shapes and the properties of the mode shapes in the next class.